Hello, IB. This is a review before you guys take your test next class. So you have already seen your review packet, and I just want to walk through some of the questions. My personal preference would be for you guys to look at the review, try some of the problems first before you look at the key that Ms. Moore and I have put up online for you guys. Obviously, a great way to practice and study for your test is to actually try the questions first, practice them several times, and then you can go back, obviously, if you're stuck, and check in with the key. We tried to be very detailed with all of our examples and working through the problems. And of course, if you ever see an issue or if we made a mistake somewhere, please always let us know. But I believe they should be in good hands for you. So the first page of your review packet is just a list of all of your different items that you need to know for this test. So just the basic idea of what a limit is, right? How do we look at it on the calculator? How do we actually find the limit algebraically? We want to simplify so that we can actually substitute in whatever the value is. If it's infinity, we would substitute a large number. If it's 1, we would want to substitute 1 for x. But we want to get our expression to a point where if we do substitute x with the number that we're approaching, we don't wind up getting an undefined value. We don't want to have any value divided by 0 in the denominator. So we always want to simplify as much as possible. Then we started this unit by using the h approaches 0 method, the limit method for finding a derivative. This is also known as the definition of the derivative. So if you're ever asked to use the definition of a derivative, it's always when h approaches 0. You guys also learned the x approaches a method. So there are 2 different limit methods you can use. There's so many different ways that derivatives are asked for you to find derivatives. Derivative, differentiation, this word gradient function. So really what you're talking about is the rate of change, the slope of a tangent line. These are all different ways of asking you guys to find the derivative. We then went into tangents and normals and finding the equations, and then there are different ways to actually approach those 2 different types of equations, or finding the different equations. So those are also, we've got a couple different questions for you in the review to remind you of that. And then you have only learned the power rule, so the derivative of x to the n. And then we also learned just the derivative of different polynomials, composite functions for the chain rule, product and quotient rules, and we also talked about taking the second derivative. All of these that are here, we will find the derivative of sine, cosine, tangent, exponential functions, logarithmic functions. We'll find those, but those are coming up the next few units. So I just crossed through them here because we're not talking about them at the moment. And then last but not least, we will be having an entire unit that deals with applications of derivatives. So we will talk a lot more about velocity and acceleration. For right now, we do just need to know that velocity is the first derivative of our position or our displacement function, and then acceleration is the second derivative. So that is our link into why do we even find second derivatives to begin with. But that's a snapshot of really what we just covered in our first calculus unit in IB. So if we walk through some of our problems, just a reminder at the top, look back over those, make sure those all look like you understand what would be asked of you. The first couple questions are very self-explanatory. Since you're asked to find the derivative, we are either using the quotient rule or the product rule, separating out your u and your v, or u and v as numerator denominator, or as first function, second function. These could both be rewritten so that we could possibly just use the power rule, or you can do 2 separate quotient rules. That's up to you as far as how you'd like to rewrite those, but I would probably suggest rewriting this one before you start. Again, number 2 and 3, you're finding the tangent to the curve. Remember your 3 steps. Find the slope, use the point that you're given, and then write the equation. We usually use the point slope form of the equation for a tangent line. The only change for normal, so keyword normal, sometimes students will skip over that word and they'll just go straight to finding the tangent line, but if you're asked to find a normal, remember we have to take the opposite reciprocal slope. And then we do have a little variation of that type of question in number 4. It says find the horizontal tangents. anytime we are talking about a horizontal line, immediately what we should be thinking is that the slope of that horizontal line is 0. And that takes us back again to Algebra 1. Our horizontal line, the slope is 0. Well, since we know the slope is 0, how does that bring us to calculus? Our derivative represents our slope of the tangent line, and therefore we would want our derivative to equal 0, which would allow you to find the point x where that actually happens, and then you can also write your equation. So there's your hint for number 4. As we're looking to our first application question, number 5, the position of an object. So again, this S of t is really the position or displacement. It's how high the ball goes, it's how far the object moves along a straight path, but they're all motion in a straight line. So either vertical up and down or left to right. That's all we can really describe the motion. It's as far as we can describe it at the moment. So find the position of the object. Well, the position of the object at time 5, we don't know if this is seconds or hours or what the unit is, but position, that means we're talking about the S function, the original function, and we're talking about time of 5. And then here it's asking for the velocity, so that means I want to find my velocity function at time of 5. And again, our velocity, remember, is our first derivative. So just remembering those links. And acceleration is second derivative if it was asked. At what time is the object at rest? Well, if you think about that ball example, when you toss a ball up in the air, or when any car or person or anything changes directions, at that moment that you change directions is when your velocity is equal to 0 and the object is at rest. So when I take my velocity function and I set that equal to 0, it'll allow you to find the time when you actually have an object at rest. When is the object slowing down? I'm going to put a star by this one because we're really going to focus more on this in the next unit, but you can start to think about this by finding the acceleration and by looking at the speed and trying to see when would the object be decelerating or slowing down or whatever you would like to say. So you can start thinking about this already, but we'll talk about it more in our next unit. For number 6, these limits are already set up for you. We're not talking about a derivative necessarily. All we're talking about here is just how do we simplify these expressions and find the limit. So if I had just substituted 3 in for x at the moment, I would get 0 in the denominator. That is not acceptable. I cannot have an undefined expression, so I want to actually find what am I approaching. So I do want to simplify this fraction and get it to a point where I can substitute 3 in to get an actual value for my limit. Same goes for 6b. Use the definition of the first derivative as h approaches 0. That means you do want to use that h approaches 0. Set up your limit. And number 8 is another question where we're asking you to just think about velocity and acceleration. So again, we're finding the first derivative and second derivative. And just start to think about what's happening along the path that this object is moving. Describe the motion. If the motion is at time of 2 seconds, well, motion would include our velocity and our acceleration because those are both moving, they're showing movement. And then at what time does the object reverse direction? We were talking about that in the last example. That's always when your velocity is equal to 0. Find the position of the object at these instances. So if it's position, I have to go back to the S function. And then think about when, again, I'm going to put a star by this one, thinking about when the speed is increasing, decreasing. We are going to talk about that more next unit, but you can start thinking about it now. Or if you've already had physics, or if you're in physics now, you can really start to think about that. Numbers 9 and 10, again, mostly review, but find the coordinates of the point on the graph at which tangent is parallel to the line. Okay, well here is a keyword parallel. Suddenly you have a question that's very similar to one you did earlier, but it's asked a different way. If you're looking for a function to be parallel, parallel, keyword from Algebra 1, means that the slopes have to be the same. If it's parallel to this line, and I know that my slope is 5 on this line, then I would want my slope to also be 5 for the tangent to this curve that we were asked to find. Since my slope is 5, that means I really want my derivative to equal 5. So if my derivative equals 5, that'll allow me to solve for x. And my hint was, what is the slope? So again, think about why would they tell you that these lines are parallel? Hint is that it has something to do with the slope. Using technology. Number 10. Please do not make this harder than it is. We are going to use our parentheses correctly. So put parentheses around the entire numerator, divide by parentheses around the entire denominator, and when you graph it, what you'd like to say is what is happening as x approaches 2. So you can trace, you can push second trace, and you can actually go right to where 2 is on your calculator as your x value. What you want to know is what is happening to the y value. So as you go to 2, as your x value, where is the y value approaching? What number is it approaching? If it approaches the same value from the left and the right, then you have a limit, and you can just write down what that limit actually is. Same goes for 1 over x. Instead of an actual number, we're asking you to look toward infinity. So if you have this picture of 1 over x, and when you guys graph this, you'll realize you get something very similar. So as x approaches positive infinity, so when it's coming down this way, what is y approaching? So as x goes out to positive infinity, which is out this direction, what value is y approaching? And as x goes toward negative infinity, what value is y approaching? It happens to be the same value in this case. And then your last few examples here. Write down the value of, and it says the derivative. Well, this is the original function. My derivative is the slope of my tangent line. Well, what would my tangent line look like if it's a straight line? What would my function be, right? So my slope of a straight line, horizontal line I should say, all lines are straight. So the slope of a horizontal line is 0. So would my derivative be 0? Another way to think of it is that if I had to write what this function was, this function is y is equal to 1. The derivative of 1 is 0. So again, my derivative would be 0. If you guys look at the second one, think about what would be the equation of this small piece here, right? I really don't care where the y-intercept is, but I know that my slope is negative 1 over 2. So if I needed to write my equation, it'd be y equals mx plus b. If I knew that my slope was negative 1 over 2 for this little piece of my function here, my b, I really don't care. It would wind up being 2, but it would be over here. If I took the derivative of this, all I would have left is the negative 1 over 2 part, my m. So what would be my slope, or the derivative, the rate of change? At 3, which is on this little diagonal piece. So in both of these cases, all you're doing is looking for the slope of those two small pieces of the function. And if you guys are given a picture like number 12, any picture at all, you know that your horizontal tangents tend to occur, all right, where on these images? And our horizontal tangents being parallel to the x-axis will occur always at the maxes or the mins. So think about what are the slopes of these tangent lines if they're always going to be horizontal because they have to be parallel to the x-axis. What would be the equations of these tangents? How do you write the equation of a horizontal line? What would be the slope of the normal of these points? So if you actually, at these points. So if I drew the normal, what's perpendicular to a horizontal line? And then last question, how could we find when any of these tangents hit the curve again? So anytime that you are trying to find when an equation, one function, meets another function, remember we always think to set those equal to each other because we want them to have the same y and the same x value when they intersect. I hope this helped. If you guys have any further questions, remember on Monday after school, I will have a review session for our test on Tuesday. And I know Miss Moore's class was reviewing yesterday and today. So I wish you all good luck studying. And please remember to attend a review session if you need it or email us over the weekend. Have a great day.